Okay, thank you. Welcome to our talk. So today we are going to present the VGPU on KVM. As we said, it's a VFIO-based mediated device framework. So this is our agenda today. We are going to cover the first. We talk about the background of this work and the motivation why we are doing this, and we talk about the overview of this framework, and then we will dive into some key areas I think people might be interested in, and then my coworker Kirti is going to take over the stage, talk about the current status, about the patches, and also we do a quick demo here, and then talk about the future work. So let's take a look at what today's GPU inside the KVM virtual machines. So obviously, we are using the VFIO device pass-through. I have the reference about yesterday Alex talk, so you can see the details there. So with this framework, yes, you get the great performance, right? So the GPU is directly assigned to the virtual machines. You completely own the GPU. And also you get a full API compatibility. So basically, because you have you have a Wonder driver running inside the virtual machine, which means the application you used to run on bare metal should just run here without any modification. So those are all good things. But there are several issues with the framework or limitations. The first one is you're completely limited by the PCI-E resource because it depends on how many PCI-E slots you have. Right? That's how many virtual machines you can run. And then another problem is because we allow the GPU directly utilized by the guest driver, by the guest virtual machine. From the host point of view, we don't know anything about this device. And this is because we are running a generic VFIO PCI driver. So the generic driver can only do some generic operations, like enable, disable, route interrupts, and etc., and reset the device, right? Secondary bus or FLR. So that's you don't have much visibility what's going on inside the virtual machine. You don't know about the usage, right? Another most important thing is for the GPU, from the GPU point of view, is it's very difficult to cover the variety of workload. For example, if you have a high-end GPU here, when you run low-end graphics workload, your GPU is kind of get underutilized. But you can also solve that problem by stick a bunch of small GPU here. But those small GPU is too small. They cannot they cannot serve the big 3D workload individually, as we said, because it's a direct assign, right? They have to work on their own. So now we have two problems. One is the visibility of this to manage this resource, and also we want to have a better sharing to cover a wide range of workload. So let's look at the VGPU solution. So this doesn't work. Oh, sorry. Yeah. So this is the high-level view of the VGPU solution. So basically, we share the physical GPU among multiple virtual machines, and it has great performance and also suitable for different workload. Right. So the way you achieve the greater performance is we have the direct communication path from the application or from the drivers inside the guest directly to the GPU itself. Right. I will cover this part later in the talk. And also we provide a full API capability because we have a Wonder specific drivers inside the virtual machine. So if you rely on some OpenGL extensions, Wonder extensions, it's all there. And also we have we have better visibility on the host. So basically, because this is a vendor specific driver, device specific driver, you actually can provide a much more device centric information like dynamic monitoring, performance tuning, and even all error reportings. Right, you can know what is going on, what kind of errors is going on inside the virtual machine. So at the end of the day, we are talking about GPU as actually it's an I/O device, right? So what we are doing here is we are trying to virtualize an I/O device. So here is I/O virtualization status today. So we have an SR-IOV device, and which was supported by the standard VFIO PCI direct assignment. You directly assign those virtual functions into those virtual machines. So with this VFIO PCI, I think yesterday Alex already covered this. So you have a established QEMU PCI driver, and it's a KVM agnostic. So as long as you are using the user APIs, you can use the VFIO framework. And it's already provided to virtualize the PCI config space and also memory map I/O space, and doing the interrupt delivery. And also it has the modularized IOMMU backend, so you can do pin and map memories for DMA purpose. That's very important for the DMA devices, for the I/O devices. So what we are doing here is we have mediated devices, which is a non-SR-IOV device, and it's required a vendor-specific driver to mediate the sharing. So it's a vendor driver's job to help to share, to virtualize the device, right? So the framework the framework we are building here is we leverage existing VFIO framework. So we use the existing user API. We maintain the existing user API, so there's no changes on that. And also we rely on the vendor driver to manage their device internal I/O resources to do the sharing, right? So here's the framework we are proposing and we are working on. So this is a common framework for mediated I/O device, right? For any I/O device which you are trying to do virtualization without SROV, I think I should apply to this framework. We have three changes, 2 new modules, and 1, you can say, enhancement or modification on the existing code. So the first one is we have a new mediated core module. We have that will basically is a provided mediated bus driver. It creates a mediated device, and also it's provided the interface for the vendor driver's callback. Because we need the vendor driver's callback to provide the I/O sharings. And also we provide a generic mediated device management interface via sysfs. That's the interface we want to provide to the user space. And if you want to build on any abstraction layer on top of that, that's what we want to do. Then we have a mediated device module, which is a common module. It's not limited to PCI device anymore. And also this is basically a driver is a driver for the previously we create mediated device. And it's also fully compatible with the VFIO user API. The last thing is the VFIO IOMMU driver. It's an enhancement. So basically means we don't change anything of the user API. We just added 2 new kernel APIs to allow the vendor driver to do pin and unpin memories. And also this because of that, you can easily extend it to non-type 1 backend. So this is the diagram I'm going to keep using through my talk. So you can see the green box is all the new modules that we are adding here. And actually, there will be one small box here, just to those 2, the new APIs, the new kernel APIs we add. But I'll add that in the following slides. You can see that. And one key takeaway here is I think you can see there's no modification here between the VFIO user API and the Type 1 IOMMU API. So basically means you can run vanilla version of QEMU. And then later we are going to do a quick demo. It's demo with vanilla I think a QEMU 2.7 Rs release candidate 2. So we are using that. So this is the framework. So let's look at how the framework actually got initialized. So the first thing you do is you register the VFIO MDEV as a driver for the mediated device later. And then it's up to the vendor driver to register his device, which he wants to use for virtualization to create a mediated device later. Right? So it's a vendor driver to register through this interface. And then vendor driver will register the mediated callback. Right? As I said before, we rely on the vendor driver to provide the I/O sharings. So there will be several callbacks we need to register for the vendor drivers here. So now we are about to create a virtual device or mediated device. As I said, we provide the sysfs as a generic interface for user to manage or to manage those life cycles of those virtual device. So let's take a quick look of what those sysfs looks like. So here's the mediated device sysfs. So after vendor driver finish the registration, you can see under the physical device sysfs, we add several new sysfs file, which is the mdev create, which is AKA the mediated device. Create a virtual device, and then you can destroy the virtual device. And then mdev support types, and you can it will basically tell you what kind of mediated device type is supported by this physical device, and what kind of configuration you can create for this device or for now. And then once you create that virtual device, then you will have this sysfs path as to represent that virtual device. And then we add this online. You can just similar to the CPU online offline operation, so you can do a start and stop the virtual device. So now let's go back to the slides. So now user can write the mdev sysfs to create an mdev device. Then you echo to like mdev UUID. This UUID has to be unique, at least per system. Then once you create that device, then you have this the device I just mentioned in previous slide. Then and this is the path. This is sysfs path. You pass to the QEMU as the VFIO device arguments. Then the QEMU will call the VFIO API and to add the VFIO device to this IOMMU container and the group, etc. And then eventually we will call the iocto, say, get a VFIO device file descriptor, right? So that you get the file descriptor back. Then once you have that file descriptor back, then it's QEM's job to access that file descriptor and present it into the virtual machine by doing the PCI config space access and also checking the bar, the memory map IO stuff, right? So let's talk about how to access the device. So this is a mediated, we said how to access the device. So the first thing I want to mention is emulated. So we do, because to make the vendor driver's life easier, right? We present for the virtual device memory region, we still present it inside the virtual machine just to keep a consistent view, right? So that most of the time you don't have to have much modifications inside for your vendor driver running inside the guest. Another thing is I have this is emulated versus pass-through. So this is not something we have added here. It's already provided with existing VFIO interface. For when you declare your region or memory map IO region, if you don't set any special flag, you will get the emulated type. If you set it as mmap, you get we can call this pass-through. So basically, you just directly map that device memory to the guest, where you want. So that give you the best performance, because whenever the application or the guest driver trying to talk to the memory map IO region inside the guest, actually he's directly talking to the hardware. There's no VM exit. So the access to the emulated region will be routed to the mediated driver on the host. For the pass-through region, you will send it to the device corresponding region, right? This is completely, in this framework, we don't put any restriction. So it's completely up to the vendor driver to implement this. Or they can say, we prefer to do the mmap at the beginning, or we prefer to do this dynamically in the runtime. So it's completely flexible. So this is how the access works. So first thing, as I said, QEMU will get a region info via the VFIO user APIs. So then That region info will eventually be provided by the vendor driver. Basically, vendor driver tell him, hey, these regions will be emulated, like normally like a bar 0 registers will be emulated, right? And then for the vendor driver, when the vendor driver access the memory map IO area of this device, it will trap into the trigger EPT violation trap here. And then when the KVM service EPT violation and then forward to the QEMU VFIO driver. Then the QEMU will convert such request from the KVM to read-write access to this MDEV file descriptor. There's nothing new here. It's just it's reused the code we have for the direct assign. And then the read-write will, by the vendor driver, then will go back to the vendor driver, right? So from the guest, now it will go back to the vendor driver on the host. So this is this device access path is normally for you to configure the device to set up device initialization, right? So once you set up this, then you are ready to launch the DMA operation. Let's take a look at how the DMA operation works in this mediated device framework. Because one important thing is we are not ISROV, so we only have single request ID. So it's up to it relies on the vendor driver on the host to set up the right mappings. So the QEMU starts. So first thing is we have to do the memory trackings. We want to track all the memories inside the guest, right? So there's no static mapping. So we don't have to set up the one-to-one mappings as we do on the like a regular normal pass-through, right? So memory region will get added by the QEMU, right? So when the guest memory gets initialized, you have the guest frame numbers, and you get into the QEMU VA space. And then QEMU will call the VFIO DMA map API via the memory listener. Right? So all the memories will add it. And one interesting point I want to make is it's not just a guest physical memory. It's also device memory will also be added into through this memory listener. But we are not going to abuse that information. So now QEMU will call this VFIO DMA map, but there's nothing get mapped physically. Then we just build a table here. We just basically say, hey, this is the VA, and we track the mapping relation between the QEMU VA to a guest frame number. And then in the runtime, when the vendor driver say, oh, I'm going to do the DMA to a specific guest physical memory, he need to call this new API to the type 1 IOMMU, say, I want to pin some specific guest frame number. So can you help me to pin that memory and translate it back? So this code will find that guest frame number and pin that memory, and also first it's get that PFN, and then send that memory back. So now the vendor driver knows what's the PFN he need to pin, or he need to map to. It's already pinned here. Then the vendor driver will call the PCI map SG to map the PFN to BFN, right? So then program DMA. So the PCI map SG will handle automatically for us is with and without the physical IOMMU here. So then the address you put on the bus is correct, right? So when the DMA is set up, then the next thing is the device is going to launch the DMA, and the device is going to notify, hey, I'm done, right? So that is through the interrupt. So that's the next topic about interrupt. So still, we go back to the initialization time. The QEMU will check to ask for the interrupt setup. So QEMU will ask query this device supported interrupt type, like INTX or MSI or MSX, like how many messages you support or how many vectors you need, etc. And this will be provided by the vendor driver. Then the QEMU, as I think Alex already talked about this in great details yesterday. So then QEMU will set up the IRQFD, KVM IRQFD, and also QEMU is going to set up the event FD, then hook up them together. Then QEMU will notify the vendor driver IRQFD via the VFIO PCI user APIs. That also will be sent to the vendor driver through this callback. Then the vendor driver, then in the runtime, when the vendor driver, because he's the guy received the physical interrupts from this device, then the vendor driver will, once he receives the physical interrupts, he's going to inject signaling the event on the event FD, which we just told by the QEMU to trigger the guest ISR inside the guest. So now let's finish the interrupt injections. So now it's Kirti.
Okay, so I'm going to cover the current status from here. So we started the RFC on the QEMU level right from the Feb, and till now we are improving. Right now the version 7 of the patches are out. Yesterday we had sent out the mail. In that, with all those improvements, all the suggestions, and like the Neo had already described, we have the 4 major patches. First one is the core driver, then the VFIO driver for the mediated devices, and the enhancement to the IOMMU driver. And we had also added the documentation how that could be used and how it will be helpful for the vendor driver to use the interfaces. While posting the patches, we had tested all these patches with the mediated device. We had tested the VGPU on the NVIDIA GPU, and we had tested all the multiple combinations, like multiple VGPUs into multiple VMs and multiple VGPUs in the per VM. We had also tested the combination of the pass-through and the VGPU in a single VM, so that we covered all the test cases here. Okay. I'm going to give a short demo how the VGPU works and how the sysfs interface works here. So this is the system which is based into our location. It's in the Santa Clara, but it's just to give an overview how it works. As like I had already mentioned that when the device is registered for the mediated core driver, we provide the sysfs entries like mediated supported types, mediated MDev create and MDev destroy. So we can use this MDev supported types to query what all configurations that the vendor driver can support. So it's up to the vendor driver what they want to define, what configurations they want to support. For example, for the NVIDIA VGPU, we support these configurations. Now I have one M60 in the system, and we support all these configurations with the VGPU M60. So right now there is no VM running on this VGPU. So it shows all the list which we can try out. Then if we decide to go with the one, so let's say we will go with the, I have a script. So we'll go with the M64Q. So I have the script ready so that we can just use it to go ahead. So for this, we have to specify the UUID for the device. Then the UUID should be unique into the system for the device which we are going to create over the physical device. By doing the echo and the UUID and the parameters, which are the vendor-specific parameters, now I am using here number 20. The 20 specifies that we are going to use a grid M64Q configuration there, and just by running the script, we'll get This will create the device. Now to check that which device has been created, it's you can see that device is created here. It's a device with the same UUID that we had provided in the first to the create. So this device is now online, and you can see that okay. Now I'll run the I'll start the QEMU. So it's just booting the Win7 VM. Now the Win7 VM is booting. I'll just get the VNC of the booted VM there. Sorry? Okay, sure. Okay, this is the QEMU command, and you can see here the device which we had provided through the sysfs. We gave the device a path there, and the device path is what we had seen, that sys bus MDF devices and the device the UUID of it. So we have to provide this path to the QEMU command line, and then it's the same as the Alex has mentioned in the yesterday's VFIO presentation with the sysfs path. It takes the device. Now we have the VM running. Okay, so this is a VNC. So it's not a remoting client. If you use a remoting client to access the VGPU devices, that it gives a very good performance. But this is what the VNC we are doing now, and you can see that driver is loaded. So NVIDIA driver is loaded and it's running, and see we had selected M64Q while creating the device. So this is an M64Q option, sorry, the device. I have one 3D app which is called a Dolphin, which is run as a test case. So this is a Dolphin running. It's running at the 60 FPS, but as I said, this is a BNC. This is not any remoting client. So if we go with the remoting client, it actually gives a very good performance here. So So this is all about the demo, and we'll go back to the slides again. So what's the future work which is remaining in this whole module? Right now we have not supported the sparse IOMMU type. We had done the enhancement to the IOMMU type 1 module, which is the Intel's x86 architecture, but we do want to support this sparse IOMMU module as well, so that the pinning and unpinning is supported by this module. Then we want to get this all interface integrated with the libvirt, so that it will be easy for the users to configure the QEMU, and it's just to configure it and run it out. So we don't have to do any of the manual work, like the way we had seen with the sysfs. So this is all we are looking for, do the future work in the very recent in the very few coming time. These are the references. So first one is the Alex's work of the VFIO that we had heard yesterday, and the links to the version 7 patches that we had already out with the code. And we had also started the libvirt discussions on the libvirt mailing list. So that includes all the details what we are expecting to be done, what is expected from the libvirt to be done. So that's it. Any questions?
Hey, one, two, awesome, it works. Hi, first off, kudos, this is the first time I actually see a sane solution to the whole how to virtualize GPUs problem. I mean, seriously, the first time I see somebody present something sane. Two simple questions. The first is, how do I get the frame buffer of that virtual GPU into my host so that I don't have to poke holes into like the guest to then fetch the frame buffer from inside? I would rather want to have it from the outside so I can then use, say, QEMU's native VNC server, QEMU's SPICE server, whatever it is, to display the contents of the virtual GPU.
Okay, I think what you're asking is about how to get to integrate to see the guest desktop through the QEMU, VNC console, or SDL, right? That is something we have in mind. But in generic one, based on the history we have seen in the other use case, that is not like a high-end accelerated interface, because most of people use this interface of GPU virtualization is directly from the guest. They have like a remote agent running inside the guest, like a Zen desktop or VMware View solutions. But for the different use case, we can look into that. How to implement this our frame buffer information. Basically, you want to just drag the pixels and the surface into the QEMU console, right?
Right.
Yeah.
Basically, I want to essentially just mmap the frame buffer that's there already, that you already like update 30 times a second, 60 times a second, whatever,
right.
and post that as like just by frame buffer into the SDL console.
Right. So first thing, I'm not aware people actually is doing like a 30 frame per second or 60 frame per second through the from the QEMU or device module console. But if there's a use case, we definitely should look into that, right? But
the main use case is it would make it work locally.
Right, it will work locally, but in our case, is most of the time when people use that, rely on that interface, it's just for the management, right? For installing driver, checking what's going on inside the virtual machine for the ID administrations, those type of work, right? So that's the case. Normally we can support that interface, but normally that interface will be limited like 10 frames per second or something like that. Okay. It's like a low frequency, low FPS interface, but there's no I mean, if there's a valid use case, we definitely should look into how to make that faster, right? As long as we don't burn too much of CPU cycles.
Right, I agree. I mean, you still have to get the memory off somewhere, and maybe you can even keep it inside the GPU memory and just really point it as a surface.
Yeah, we do. We should be able to DMA directly to frame buffer back to the memories you need.
Well, again, you don't really have to, because you are eventually you actually are overlaying, right? You could just use an XV interface, XV style interface. This is all like old times. These days you do it differently. But something that keeps your memory inside the GPU, so you don't have to flush it out to memory all the time, which then again burns all your PCI Express cycles. The other one, and I think that would be really cool, because then I could just say on my notebook with the NVIDIA GPU, go and run any random VM and just have a window with fully accelerated graphics in there.
Right.
That's basically what's missing on that solution. The other part is for DMA accesses. I remember from the Intel stuff that they went through great lengths to make sure that they isolate all the separate contexts they have in their internal AMU, so they switch them the whole time and make sure that they have different IDs and different page tables for them. Do you have something similar on yours?
We don't have that.
So basically, one guest could access another guest's memory?
Oh, no. No. What I'm saying is that we don't have restrictions to put them into the different VA space, right? But because we have a GPU, have an IOMMU as well. So we fully rely on the GPU IOMMU to isolate those contacts. So they cannot access each other's memories.
Okay, so they are isolated. They can run in parallel. You basically have virtual IDs inside your IOMMU and multiple contexts to inside the IOMMU.
Yeah, we have multiple.
Yeah, that works then. Cool, awesome, thank you.
Thank you.
In the sysfs interface, you have a supported mdev types file,
yes,
which lists various different things you can create.
Right.
Unless I'm missing something, it didn't say how many of each you could create.
Yeah, we have. There's a maximum account or max. I forget the term. It's a max instance or max account. That is how many you can create.
Okay.
Yeah. Also, it's inside the name, but we do have a specific column say.
And presumably, if you create one of one type, that's going to decrement how many you can create of all the other types as well.
Right. So far, we don't support a mix match types. So once you create one type, so if you check that file again, it will just show you this physical GPUs can only support that type.
Okay. Thanks.
Yeah.
And there seems to be kind of two levels to this. There is a generic type of or device type that you introduce,
right?
And then there's the specifics for graphics devices.
Mm-hmm.
Do you have a plan to kind of separate those two so that other types of devices that doesn't have resolution or stuff like that could use it?
So far, actually, the framework we are building here is should apply to a generic I/O device. I don't see anything else other than what Alex just asked to extract the frame buffer outside to the QEMU. That it will be graphics specific, right? But for everything else here, it should be generic, I think.
It's working? Intel did a similar things. I think we presented at KVM
right.
for 2 years ago.
Right.
And just wondering if and basically the approach is the same. Basically, we used a mediated driver.
Right.
So the question is there any framework, anything is shared or?
Oh, yeah, sure. This is like Alex said yesterday. So this is a collaboration work between NVIDIA, Intel, Red Hat, and also IBM. So yeah, it's very well discussed.
Okay, that's good. Yeah. And then the other question is you may need some scheduling if you have multiple graphics
yes.
controllers, and that's being done in vendor-specific driver, or?
There's actually two parts of scheduling, right? So one part is the guest scheduling. Like for example, if you run Windows VM, you run WDDM, all right? WDM is basically schedule the graphics workload for you already, right? So we don't want to touch that part, right? And there's the second part of scheduling is on the host. So it's completely owned by the vendor-specific drivers. In our case, it's NVIDIA GPU, and we program our hardware, and we do the schedulings, and we will try to achieve the best performance for the fairness, right, or the QoS thing.
Okay.
Yeah.
And then do you do some over subscription? For example, partition the GPU resources and then I think assign those, or do some over subscription?
So yeah, it really depends on what kind of subscription you mentioned here, right? So let's say if you said, do you support a frame buffer over subscription, right? Yes and no, right? So if I say yes, it's because Windows support that already. So if I give you a 12 megabyte virtual GPU VM, you actually can run much more workload than the 12 because Windows will match the page in and page out already automatically, right? But on the other hand, we don't support over-subscription on the host. You can see the number of virtual machines you run actually is limited by the size of frame buffers of the physical card.
Okay.
Right? So yeah, that's two parts.
Okay, thank you.
Hi. In your presentation, you didn't mention that you are separating the control path and the data path. So is that something that has been done, or you're not looking at that part?
The control path is, let's say, this is not true. This is not anything new for virtualization, for the virtualization, right? Even you program the I/O device or graphics workload, we wanted the control path will be very short. You just set up everything. Then the next thing is the data path. You basically just shuffle your commands to the GPU directly. So those two parts is already separate. In the bare metal, how you program the GPU, we just preserve that attribute, and we just make sure when you want to shuffle the commands to the GPU as fast as possible, we don't have any bottleneck in this virtualization framework.
Okay.
That's what we did.
Right. And my another question is that you mentioned that based on the memory accesses, it can be either passed through or
Emulated.
Or emulated. Yes.
Right.
So that means even dynamic switching is also possible?
Sorry, what? Oh, that dynamic switching.
Yeah. At presently, I'm using as in a pass-through mode, and if I want to switch to emulated mode, that way.
No.
I don't think so.
No, it's not dynamic. It's not dynamic. You have to. The vendor driver needs to specify it at the initialization itself. So when VFIO API queries about the get region information, at that time only the region information, the flags has to be set at that time only, and that's done at when the QEMU initializations.
So initially, it's the vendor driver that needs to provide this information.
Right.
Okay, that's fine. Thank you.
Hi. You mentioned that one of the advantages of the mediated versus full pass-through is the control of the host. But I don't see any kind of configuration. What can you do? What's the flexibility of the configuration? Can you reduce the CUDA core inside one VM and assign to another? Can you change kind of the coder hardware stuff and assign to a virtual machine instead of another? What's the flexibility of the configuration?
Sure. Yeah, one thing is I think June already asked the question about scheduling, right? So what we can do here is we can have more better scheduling algorithm here because we have the host vendor-specific drivers on the host, right, on the device. Right, so you don't have to fully just rely on the virtual machine itself. That's one part, and also we can have a better monitoring, right? So you can monitor what's the usage workload of that device. It's not like so the CUDA core is not like something you can dynamically add and reduce.
Okay. Yeah. And another question is, how can you use the GPU power on the host to do some computation or whatever, or you have to create a virtual interface and assign to the host?
Right. That's a good question. So for now we don't support that. So basically, what you are saying is are you still going to run the graphics workload on the host, right? As a client type of virtualization, so you can support the virtual machine, and also you have you have a local graphics workload supported by the GPU. So far, we don't have that support. No, this is a server. It's mainly for the server market, and it's I shouldn't say those are marketing stuff, but this is mainly for the secondary GPUs. Right.
Is there a particular reason that you decided to do this software implementation rather than doing it in hardware as an SRIV device?
One thing is expensive. Right. We want to prove the market. We want to then burn something in silicon. Right.
I have a very simple question. So currently the physical GPU hardware was shared by multiple VMs, right? So my question is currently how many VMs can share the same hardware?
It's like in today's in the current release, we support 16 virtual machines.
16.
16, 1/6.
So how about the performance? Like the total performance compared with the native?
The performance is it depends, right? So if I want 16 virtual machines, and I run like a Unigen Heaven, right? So that probably don't get the best performance as you have on the bare metal. It depends, and also it depends on the application you have. It's a CPU bound or GPU bound, right? Yes. If it's a CPU bound, then you should get a better performance compared to the bare metal.
Okay.
M16 is on M16 or K100?
M16. I think that's it. Okay, thank you.
Thank you.